Thanks, everybody, for coming out tonight. I'm really excited to be able to do a little kind of pop science talk relating to the Marvel Universe. So a little bit about me and my background. I'm trained in classical synthetic organic methodology, which means I come up with reactions to put things together. So I like to build stuff. And during the course of my graduate work, I ended up working in the area of macromolecular chemistry. We designed chemical sensors for glucose. And I did pretty much everything in that project from the ground up. So basic small molecule synthesis, polymer work, and lots of analytics to see how the system functioned. So I got very familiar with what is typically referred to now as either supramolecular chemistry or macromolecular chemistry, which means looking at things more in large constructs rather than in small molecule form. And when you get into these macromolecular designs, you get into the nano world. So that was kind of my first intro to nanoscience and nanotechnology, was working on these chemical sensors. Then, as a postdoc, I actually made lots of different nanoparticles, and we tried to use these nanoparticles to basically cap the top of an HIV virus. So we were targeting proteins and trying to attach sugar molecules to these proteins in very specific patterns, and the way that you create these patterns on very small scales is by using techniques from the nanoscience world. So again, we're working down at that very small scale when we're working on nanoparticles. So the last probably 10 years or so, I've taught organic chemistry, so the fundamental concepts and ideas for putting molecules together that then lead to these much larger macromolecules. And I really liked the Marvel Avengers movie here because it gave me a lot of material to talk about from many of the different Marvel characters and how some of what we see on screen relates to the nano world. So I'm not going to sit up here and try to disprove any of this, right? This is all comic book world. But there are some really interesting discoveries that have been made over the last probably 2 decades in the nano world that does directly relate to a lot of what we're seeing here. And interestingly, you don't see any of this nanoscience, nanotechnology being talked about in comics or fantasy, probably until about the late 80s, early 90s, because there was no nanoscience, nanotechnology until about the late 80s, early 90s. So this is actually a really new field in material science. But before we jump into some of that quick history and some of the applications, let's just take a quick look at what the nanoscale is. So if we look at small molecules like water, or say a sugar molecule, we're looking at something that's on the order of a nanometer. Small molecule like water, where you've just got a couple of atoms of hydrogen and oxygen, a little bit smaller than a nanometer. We get into a sugar molecule, which is significantly larger. You've got 6 carbons, 6 oxygens, and a bunch of hydrogens on there. And now we're at about the size of a nanometer. So the nanometer scale is about the scale of a chemical bond. When we start talking about bond distances, we're talking about basically nanometer distances. Usually when we talk about single atoms, then we go down to the angstrom, which is 1 unit smaller than a nanometer. Something like a virus is about 100 nanometers. So when I was working on HIV viruses, I was working on a virus that was about 100 nanometers, and the particles that I made were about 2 nanometers. And we would tag these viruses with those 2 nanometer particles. We get into slightly larger things like bacteria and cells, and then we're at 1,000, 10,000 nanometers. A pencil tip, 10 to the 6 nanometers, and then we get into something like a tennis ball, and we're pretty big here, 10 to the 8th nanometers. These are kind of common constructs that we use at the nanometer scale. Something like a dendrimer, which is really just a highly branched sugar molecule, is going to be typically 10 to a couple hundred nanometers. Quantum dots, which are really, really interesting in electronics, down at the nanometer scale. These were discovered probably in the early 80s as one of the first examples of nanoparticles that were characterized, measured, and evaluated. I worked a lot with gold nanoparticles. Gold nanoparticles and silver nanoparticles are really easy to make and produce, and you'll see a lot of this usage. And then we use metal oxides and then get into some bigger nanometer scale scaffolds like liposomes and polymers. Now, there are some nice historical examples of nanoparticles in art and weaponry. And if we go back to 4th century, we can look at this dichroic glass, the Lycurgus cup, which has colloidal silver and gold particles dispersed into the glass. So you take some glass, and when you're heating that glass up and forming it, you fume a little bit of gold or silver in, and you get this colloidal dispersion of nanoparticles, which have a big effect on light. If we look at the cup from the outside with light, it appears green. If we put a candle or some light inside of the cup, then you get this really interesting red glow to it. Other examples of nanoparticles in art historically are things like the stained glass windows in cathedrals like Notre Dame. I believe this is the rose window at the Notre Dame Cathedral. There are dispersions of nanoparticle gold chloride, which give the luster. They also act as photocatalytic air purifiers. It's kind of an interesting little side effect of the gold nanoparticles. If we look at some examples from metallurgy, something like Damascus saber blades from 3rd through 18th century Middle East contain carbon nanotubes in cementite. And this is a really nice example because we can actually look using something called an electron microscope down at that nanometer scale and see the carbon nanotubes that are embedded in this blade. These blades were extremely tough and also had a very distinctive luster from that nanoparticle dispersion within the metal material. So those are, like I say, some nice examples from kind of art and historic. But now we get into more modern time, and we have kind of dawn of nanoscience. And like I say, the field of nanoscience, nanotechnology, is really in its infancy still. In about 1857, Michael Faraday showed that you could get these colloidal gold dispersions in solution, and based on how you made the colloidal dispersion determines what your particle size is. You get different colors from these colloidal golds. So this is now known to be caused by the size of the nanoparticle. In about 1936 here, mid-30s, Mueller starts to develop field emission microscope. And then another really key event happens in 47. We get the semiconductor transistor out of Bell Labs. The reasons that these are really key is we start to be able to see at levels that we couldn't see at before, and we can start to do computations. Then, about 30 years later, a few things happen in between. Somebody actually uses the term nanotechnology in a talk. Taniguchi in I believe, University of Tokyo, and he's referring to machining materials at the atomic scale when he's referring to nanotechnology. There still isn't a field of nanotechnology or nanoscience. There are just people kind of doing some stuff and making some observations. I worked with a few chemists that were trained probably World War II, Korean War era, and what they would joke about all the time, because this was now early 90s, what we're developing here as nanotechnology is what everybody threw out, because nobody could see what it was. You either made small molecules, and you isolated small molecules, and you characterized the small molecules, and then you passed those off, or you made polymers. The garbage that came out in between was thrown out until you have things like scanning tunneling microscopes invented in the early 80s, which allowed people to start to observe things down at the atomic scale. Now we could see what's going on, and we start to be able to pattern. Then in 1985, a really key event, the Smalley lab discovers Buckminster fullerene, or buckyballs. Buckyballs are an allotrope of carbon. An allotrope is a naturally occurring form. Most people are familiar with diamonds and graphite, but buckyball was observed for the first time in 85. Very quickly, he won the Nobel Prize for this discovery. You'll see that this nanoscience moved very quickly into the technology world, and a lot of these contributions were recognized very quickly and early, and Nobel Prizes were awarded very, very quickly compared to other fields. So then quickly thereafter, we get atomic force microscopes, and these have the ability to view and manipulate materials at that nanometer scale. So now we can start to pattern at the nanometer scale. Again, semiconductor, really important, because this then led to information age and the development of microprocessors. And I'm sure a lot of people are familiar with Moore's law and the doubling of processor speed with the reduction of size and cost. Well, a lot of the ability to increase processor speed and reduce the size is due to our ability to start to pattern at that nanometer scale. It is kind of going along the nanoscience, nanotechnology with the development of microprocessors and computer science. So then, some scientists at IBM used that atomic force microscopy to actually spell IBM with single atoms of xenon on a chip. And, well, these things seem, like, who cares? It's the first example of being able to do something like that, to be able to manipulate at the atomic scale. And it starts to show just how powerful this nanoscience and all of this nanotechnology is. Then we get carbon nanotubes in 91. Again, these were around. Nobody had observed them because you couldn't see at that scale. So it was really critical that we had these tools to be able to see at this scale and then go ahead and use those same tools, kind of changed around a little differently, to manipulate the material at that level. So we get things like nanolithography. So in lithography, we use some masking and put down a pattern. We can do the same thing at the nanoscale using some AFM modification and get these patterns at the nanometer scale. Shortly thereafter, late 90s into the 2000s, nanomaterials start to find their way into consumer products. We see a lot of use of nanomaterials in automobile manufacture. We see nanomaterials being incorporated into sporting equipment. We have things like nanoparticles of silver being used in socks and other clothing items because of their antibacterial properties. Nanoparticles give fantastic strength with low weight. So they end up being incorporated into a lot of other plastic materials and coatings because of these properties. Another really key event happened just a few years ago. In 2016, the Nobel Prize in Chemistry was awarded to Sauvage, Stoddart, and Ferenga for their work on molecular machines. It is essentially the early use of nanoscience and nanotechnology. And a lot of what they did early on seems very simple now compared to what they're doing. But these were really key fundamental discoveries that were made. So they took basically a couple of ring systems and tie the ring systems together so that you have these interlocking rings that then rotate back and forth. Or you have something that travels along a polymer like a piston, again, something that rocks back and forth at the molecular scale. So these were really interesting molecular machines. They've been refined and developed much, much further. You see things now like nanoscale cars that they can actually measure movement by changing temperature on a plate. You can get these catenane systems to flip around each other by changing light frequencies or changing the heat temperature. And these are now being used potentially in development for things like quantum computers. These can work as switches at the molecular scale for computing, which is, again, a really interesting area that has kind of come out of this fundamental nanoscience. So now let's turn our attention to how some of this is incorporated and related to Marvel Avengers. So first, we've got our cyborg robot Vision and all of the amazing biomedical science that's coming out of Wakanda. Well, in order to create some type of a cyborg, we would have to have an immense amount of computing power, something like quantum computing. So that would be nanoscale computing processes that are all combined together to create this cyborg-type system. And here's an electron micrograph of an IBM quantum processor. These are currently in development. This is, I believe, a 7-qubit processor. They've used these qubit processors to solve what we call the Schrödinger equation for things other than just hydrogen, which for a physical scientist is really, really impressive because these Q processors can handle more than just yes and no. They can handle yes and or no at the same time. So they have the ability to function a little bit more robustly than the digital processors that we currently have. Also, we can get them to operate much faster. So Nebula, another example of some cyborg technology, which would have to incorporate some nanotechnology in order to create this type of a cyborg system. Now, when we go ahead and watch the movie, we're going to see Nebula is basically pulled apart at some point, but then all of her circuitry manages to snap back together. So in order to accomplish something like this, we would have to have some flexible microelectronic processors. And in fact, there are examples of self-healing polymers in the literature. So using some coated nanoparticles, we can break them apart, and then we can get them, to both mechanically and electrically heal and anneal so that they're functional again. So again, in order to reattach some kind of a cyborg arm on somebody like Bucky, the Winter Soldier there, we would have to have some kind of a self-healing polymer, which we could potentially imagine coming out of some of this nanotechnology. And here is, again, electron micrograph of both a damaged and then a healed polymer that's been subjected to some stress. So again, another reason I really like this movie is that we have the Guardians of the Galaxy and all of their silliness, but we have Spider-Man, who's by far one of my favorite Marvel characters. So let's talk a little bit about the spider web. And there's actually a bunch of different types of spider web, and we'll focus on the major ampullate silk gland, which is usually structural and dragline. So first, Spider-Man shoots web. Spiders don't shoot web. Spiders use gravity to pull web. So I would argue that Spider-Man's web is a synthetic and that it is being, produced by some kind of an external device. It's not being produced internally because he's not producing it the way that a spider does. If we do look at spider web, we can see the nanometer construct there. We have these very smooth fibers at the nano level. There are only actually a couple of different protein sequences that are typically used, and then these protein sequences are cross-linked by secondary interactions to give that nanometer-sized fiber. But that spider silk is incredibly strong. Strength 1.1 gigapascals is comparable to steel, not quite as strong as carbon fibers, which again are synthetics. But if you go to Dr. Rhett Allen's reference here in Wired magazine, he's a physics professor at one of the schools in Illinois, I believe. He went through and went ahead and did a quick calculation as to what type of tension Spider-Man's web would need, and it would require about 39,000 newtons of strength in order to do something like hold a car. So 39,000 newtons, spider silk isn't going to cut it. Again, we're going to have to go to some kind of a carbon nanotube rope. Carbon nanotubes will give you about 1.98 times 10 to the 5th newtons. So that would give us the strength we need to hold a rope or to swing from building to building, I suppose. So another important aspect of the Spider-Man is his ability to cling to buildings. And we know that spiders can, in fact, climb up walls. And the reason that a spider can climb up a wall is that on its leg, it has these tufts of hair, and each of those tufts of hair is covered by thousands of smaller hairs called sexuals. Those sexuals are just hundreds of nanometers in width, and it's that combination of sexuals which gives the surface tension required for the spider to stick to the wall. Another place where we see these sexuals used is in the gecko adhesive system. So we could look at the gecko adhesive system at the macro, meso, micro, or at the nano level. At the nanostructured level, we see thousands of these little sexual tips, just like we see in a spider's leg. So we could have some kind of a gecko type of glove or sock, which would allow us to stick to walls and climb up it. And some folks have actually taken the idea of the gecko sexual and made a synthetic version of it, and then taken this synthetic version, coated it onto the tires of a toy car, and then showed that the toy car would stick to plexiglass. So I think that's a really nice example of using bio-inspired design in the synthetic lab to produce a modified fiber that would allow you to climb a wall like Spider-Man. So now we'll turn our attention to some of the technology involved in maybe the suits. We've got all of these fantastic suits. We've got the Black Panther's suit made of vibranium. Well, the material that I know that stops bullets and has got high strength and flexibility is Kevlar. And we can take Kevlar, which is shown here in A and B. The problems with Kevlar, it stops materials well, but it still takes all of that force brunt. If we impregnate the Kevlar with nanoparticles, which are C, D, E, and F here, we change the properties of the Kevlar. The Kevlar actually starts to spread out the force of impact as you impregnate it with nanoparticles. So somehow these suits have to spread that force out. Maybe they incorporate some other type of nanoparticle into the system in order to change the property of the material. Now the problem is, how do you get the suit to grow? As Iron Man's and Black Panther's suits just kind of appear, so does Spider-Man's now, I believe. Well, we can also look to some bio-inspired armor. In the biomineralization process, we get this very patterned growth, like in the abalone shell. We've got nice aragonite formation in abalone shell. Starts off as a small platelet, and then the nanoparticles grow off of that initial platelet, so that you eventually have this very tightly woven nanostructure. But it's kind of interesting because in some cases, the vibranium seems to be very flexible. In other cases, we've got very, very hard vibranium. Again, the only way I could explain something like this with the same material is that one of them has to be impregnated with something, the other maybe just the material as intact. So we also have some nice examples of synthetic versions of something like aragonite formation. We can use that same idea that we see in the abalone shell and grow synthetic films that have similar toughness and high flexibility. And then I just wanted to kind of wrap up with some of the energy production that we see in things like the Iron Man. In order to be able to produce and contain these blasts, we would have to have some way of energy production at the nanoscale. And again, we have some examples. We could use something like these molybdenum sulfide coated silica films, which have been shown to produce hydrogen gas by photolytically splitting water. A lot of these nanomaterials will act as photocatalysts. So we could produce some hydrogen gas. We can pump that hydrogen gas maybe into a fuel cell in some kind of a nano-encapsulated environment, and then generate energy that way. We would also have to be able to store this energy, and there's a lot of research in the nano world on energy storage. So we get a lot of these metal organic hybrids, which are used in new solid-state batteries, which are good for ultra-high energy storage and could potentially contain the energy of something like the Infinity Stones, so that we could then use that energy on demand to blast the universe, I suppose. So those are just a couple of the little highlights of nanotechnology that I wanted to share with you, which I found that kind of relate to the Marvel Avengers movie. I hope as you watch the movie, and hopefully as you go and watch the Avengers Endgame coming out in a few months, you'll think about what's going on with the science behind these things a little differently. Maybe this will pique your curiosity or get your imagination going, and you'll become interested in potentially pursuing some of this kind of research. Because, like I say, nanoscience is really at its infancy. It's about as old as I am, as far as being able to really look at the materials and manipulate the materials and make really functional products out of these things. So there's a lot of space and a lot of room for anybody to jump in and potentially have a productive career in this area. So I'm going to go ahead and stop now, and if there are questions, I'm happy to answer. I'm not sure how much time we have before the movie needs to start, but like I say, I'm happy to answer questions. I'm not an expert at all of this, but I do have some knowledge, and I'm happy to answer whatever questions I can. Otherwise, I'd like to thank Samantha and Michael for having this event, the Eureka Theater here for putting this on, the grant funding agencies, and of course everybody for showing up again tonight. I hope you all enjoy the movie.